pot
Lose
pie
at this
day.
point.
Math is like pot pie because it's got a lot of identities, and pot pies have a lot of ingredients. So welcome back to math class. We're going to do more on identities. Remember, on this section, when you work with these problems on the proofs, you have to work with the left side only and not the right side. So you work with the left side all the way down until you get it equal to the right side, and then you've completed the proof. Also, make sure your work is going down, not over to the right. You really want to line things up as you go through these. Take a look at the first problem. This is number 48 out of the problems in the back of this section. Sine theta times cotangent theta equals cosine theta. The directions are to show the left side equals the right. How do you show the left side equals the right? You pick it apart until you get it to equal the right side. So how can I pick this apart? Well, the cotangent theta can be broken down into the ratio identity. So I'm left with sine theta times cosine theta over sine theta. Notice nothing's written on the right side. At this point, it's a multiplication of fractions. You can think of this as sine theta over sine theta. They divide out, leaving ones, and you're left with cosine theta is equal to cosine theta, and then you're done with that identity. Going on number 54, same idea, break it down to try to get it to equal to the right side. The right side is really 1 over sine theta, so if I can get the left side just in terms of sines, I'm done. So how do I do that? Well, secant theta and secant theta is unfriendly. Tangent theta is actually unfriendly in this one as well. I just want it in terms of sine and cosine. Ultimately, it's got to be sines on the left side. Let's go ahead and break that down. Reciprocal identity on the top, ratio identity on the bottom. At this point, you can multiply by the reciprocal, or you could also think of multiplying top and bottom by cosine theta, either one. You want to show your work on how you're getting from one step to the next. At this point, you're going to get 1 on the top and sine theta on the bottom. I'm still not done with the reciprocal identity. That's equal to cosecant theta. And you just completed the proof on that one. Moving forward, again, you should have these main identities in front of you as you're following along, picking them off of that big rock sheet to make this easier. And then for the quiz and the test, you're just going to have to know all these identities by heart because you're going to use them later on in the book. Number 60. Same idea, show the left side is equal to the right. Cosine theta times tangent theta plus sine theta equals cosecant theta. Pick it apart, and the way you're going to do this is the cotangent theta doesn't look very good. So we want to change that, therefore it's cosine theta times cosine theta over sine theta, which is a ratio identity. That becomes a multiplication of fractions. Therefore, cosine theta times cosine theta is cosine squared theta. You want to add these fractions. And as you add the fractions, you need the same denominators. Therefore, you know you have to have the denominator of sine theta over here. So I'm going to multiply by sine theta over sine theta, which is 1. Now I can combine the two fractions, and it becomes cosine squared theta plus sine squared theta all over sine theta. You know it's got to be simpler than that because the right side boils down to 1 over sine theta. Or maybe in this case it should be bakes down to instead of boils down to, like hot pies. And then we have, cosine squared theta plus sine squared theta equals 1 with the main favoring identity, 1 over sine theta. And then with the reciprocal identity, we have cosecant theta equals cosecant theta. This is a good problem. It involves fractions, involves reciprocal identities, Pythagorean identities, ratio identities. Let's go to the last problem. Last problem is, if you pay attention, you'll see that these become relatively easy, but you need to know the process in doing this. And the directions are to substitute your x equivalent into x and then simplify the radical. And so to do this, the first thing you're going to do is the substitution. You want to see exactly what you're dealing with. Be very careful with parentheses. With the usage of parentheses, I'm not going to make the mistake of not squaring that 5. It squares everything that x is equal to. So at this point, it becomes 25 minus 25 sine squared theta. You want to be able to pull out numbers of this radical. The way to pull out numbers of a radical is to look for perfect squares. But in order to pull out perfect squares of a radical, they have to be multiplied under the radical sign. The idea is that if you had the square root of a squared times b, notice that a and b are multiplied here. This is multiplication. It's the same thing as square root of a squared times the square root of b, and that's going to equal absolute value of a times square root of b, which I'll talk about in a little bit on why that's absolute value. But the main part is you're looking for multiplication under the radical, so you can then pull out the variable or the number. If you're adding or subtracting, you can't do that. Therefore, back to the problem, this only gives you one idea, one thing to do, which is going to be to factor the 25 out. So that's the main step in doing this problem. It's kind of the trick. And you would have 25 times 1 minus sine squared theta. Well, this problem is going to boil down to a pretty easy number here, which is going to be just 25 times cosine squared theta, because we just did a Pythagorean identity here. 1 minus sine squared theta equals cosine squared theta, right? If I did this in shorthand, it would be cosine squared plus sine squared equals 1. Well, if I subtracted sine squared from both sides, I would get this identity, and that's what I'm substituting in for that right there. Over and over, you're using that Pythagorean identity. Therefore, I can now extract the squares out of the radicand, and so this is going to end up being 5 times the cosine of theta. And in the book, you're going to notice that they're going to have an absolute value around the cosine theta. The reason why they have an absolute value around the cosine theta is because the cosine theta has to be positive. Up at the beginning, this means that you're going to have a positive number all the way down. It can't be negative when you take the square root of something. It's always going to be a positive number. So because it's positive, this has to be a positive number at the end, which means cosine theta has to be positive. You see, if you substitute angles in for theta, you can get a negative cosine theta, and that would make this negative. So the book is very particular in saying, I don't want to be negative, so I'm going to put absolute value around cosine theta, so it's always positive, and therefore this will always be a positive number. Now, for me, if you can do all this work and get down to 5 cosine theta, you're perfectly fine. So if you see this as an answer in multiple choice, or this as an answer in multiple choice, both of those will be correct. Not just one way to make a 5. That's that's all for today, and just remember that we've got a quiz on Friday.